This is me. In my first year of college, I took multivariable calculus, a course that many of you may be familiar with. When I was taking the class, my roommate, let's call him Ari, was a physics and CS double major. He had taken the course before, so he offered me these words of wisdom.
The way that multivariable calculus all comes together at the end is just amazing.
Now, let me tell you, even after taking the class, I had absolutely no clue what Ari was talking about. Despite all of the long nights of double integration and essay writing, true story, we wrote essays for calculus, I still didn't get it. The problem was, I understood all of the theorems and concepts individually, but I couldn't see how they were all related. And I think that's a boat that a lot of students are in. Seeing connections between things is all about perspective. I can show you thousands of pictures of the Earth, but you'll never gain the perspective that astronauts have when they look down on our planet from thousands of miles in space. What Ari was describing, this idea that multivariable calculus all comes together somehow, was a perspective. And in this video, I'm going to present that perspective to you by building multivariable calculus from the ground up. So, let's get into it. I'm going to talk about 5 different theorems here. The Fundamental Theorem of Single Variable Calculus, the Fundamental Theorem of Line Integrals, Green's Theorem, Stokes' Theorem, and the Divergence Theorem. Theorems 1 and 2 are very similar. 3 is actually a special case of 4, and by the end of the video, you'll see how all 5 of them are really the same thing. As we build up from one theorem to the next, we'll work with higher dimensional objects and spaces. As a disclaimer, I'm not going to spend much time rigorously proving these theorems. It's not important for this video, since we just want to see how they're all related. Let's start with the Fundamental Theorem of Single Variable Calculus. The formula for this theorem can be written like so. What this is saying is that the difference between the value of a function f at x equals b and its value at x equals a is equal to the integral of its derivative from the bounds x equals a to x equals b. To build up calculus from the ground up, I'm going to break this formula down step by step. We can write the derivative of f in prime notation as shown, or in Leibniz notation like this. Leibniz notation essentially writes the derivative as a quotient, df divided by dx, where df is a very, very small change in f, and dx is a very, very small change in x. Mathematically, derivatives are not actually quotients, but writing it this way can help us understand the geometric intuition behind this formula. Let's consider the graph of f versus x. Here I just chose f to be a random curve that is both continuous and differentiable along the interval a, b. What that means is relevant for proving this theorem, but not too important for our intuitive explanation. If we look back at our theorem in Leibniz notation, we can sort of pseudo-cancel the dx's to get just the integral of df from a to b. Mathematically, you can't actually do this. Df dx is not a quotient, but an operator ddx acting on f. But we'll write our formula like this just to help develop intuition. Remember that df is a very, very small change in the value of the function f. Infinitesimally small, in fact. Graphically, this would correspond to a vertical movement from one value of f to another. So we understand what df is. Now let's check out the rest of this truncated formula. Integrals can also be thought of as infinite sums. In our case, this integral means we're adding up an infinite number of infinitesimally small differential components df. So this integral is really telling us to add up all of the infinitesimally small changes in f from x equals a to x equals b. The sum of these tiny changes in f from a to b is just the total change of f from a to b. And so we can see that the integral of df from a to b is the same as the difference between the value of the function at b and its value at a. Now let's rewrite our theorem the way it was originally written with Leibniz notation. Just as df was an infinitely small change in f, dx is an infinitely small change in x, which would be a very small step in the horizontal direction on our graph. You might have heard that df dx is the slope of a tangent line to f at a given x. This makes sense. df is our vertical rise and dx is our horizontal run. And if we divide rise over run, we get the slope. To get df, we just have to multiply that slope by the corresponding dx at a given point. So really, when we're taking an integral, we're summing all of the products of the slopes times their infinitesimal runs from a to b, which is the same as summing all of the infinitesimal rises from a to b. The reason we have to consider each infinitesimal dx is that the slope, df dx, changes slightly at each value of x. When we describe the fundamental theorem in this way, we've essentially broken down the ideas of integration and derivation completely. Integration is the infinite summation of infinitely small components, while derivatives are simply slopes. Multiplying a slope by an infinitely small run gives us an infinitely small rise, and taking the infinite sum of all the rises gives us the total rise. And that total rise is the net change of our function. I'll say it one more time just for emphasis. Multiplying a slope by an infinitely small run gives us an infinitely small rise, and taking the infinite sum of all those rises gives us the total rise. And that total rise is the net change of our function. So that was a lengthy, intuitive description of the fundamental theorem of single variable calculus. We can, of course, make this description even more concise, and that will be of great use to us in understanding how multivariable calculus all comes together. But it also means we have to make a sacrifice. Unfortunately, in higher dimensions, this simplified description of integrals and derivatives doesn't quite hold up. Our derivatives aren't always going to be slopes, and our integrals aren't always going to be infinite sums along axes, but instead infinite sums over new, weirder shapes. We'll get into what that looks like, but for now, this just means that it's better for us to describe the fundamental theorem of single variable calculus not with the dimensionally restricted concepts of slopes and sums, but with the more abstract ideas of derivatives and integrals. So with that, let's put this formula into words. The integral of the derivative across the bounds is equal to the original function at the bounds. Keep this sentence in the back of your mind. We'll put it aside just for a moment in our formula dictionary, a set of conversions of calculus formulas to plain English. We'll continue to add to this dictionary over the course of the video and get back to it near the end to answer our overarching question. Now, let's discuss line integrals. From the name, they suggest we are taking the integral over a line. But what exactly does that look like? Well, for our purposes, we're going to be looking at line integrals of vector fields. You can think of a vector as an arrow with a magnitude or size and a direction. Vector fields are kind of like functions that output a vector to each point in space. The line integral of a vector field over a curve C is calculated in a similar way to the integral of a regular function. For the 1D case, we multiply something, in the fundamental theorem that something was the slope of the tangent line, by tiny changes in x to get a tiny change in y, and add up all those tiny changes in y to get the overall change in y. For the case of our vector field, our tiny changes in x are now the vector derivative of our curve C. C is a vector-valued function, written as r of t, which is similar to a vector field, except now each point on the curve C is defined by a vector that points in the origin to a point on C. Because C is vector-valued, it defines the x and y coordinates of its points in terms of a new variable t. So we have derivatives in both the x and y directions, which together sort of make a derivative vector, r prime of t. We take this derivative vector and multiply it by the vector in our vector field at a given point. Except we can't multiply two vectors, so instead we take their dot product. Adding up all of these dot products at different points along the curve C gives us the final value of our line integral. Mathematically, this idea can be written like so. Our something is now a vector field. Our tiny changes in x are now derivative vectors of C. Our tiny changes in y are now dot products, and instead of adding all the tiny changes in y, we add up all the dot products to get our overall line integral. The bounds a and b are now the endpoints of our curve C. The x and y points inputted into our vector field are often just written as r of t, because those are the points on our curve C. Oftentimes, we can also truncate this derivative vector to just dr, to better represent the idea that this is a derivative vector. And finally, We usually don't write the bounds of our integral as a and b, but instead just write c at the bottom, indicating to take the integral over the whole curve c. If this description was confusing, that's because I glossed over a few important details, but don't worry about that for now. I'll make a video later explaining line integrals in much more depth. For now, let's take this idea of taking the integral over an arbitrary curve for granted and examine the bigger picture. The reason we care about line integrals of vector fields is that the gradient of a regular multivariable function is a vector field. Well, then what the heck is the gradient? When we have a function with multiple inputs, a multivariable function, we don't just have one derivative. We have many partial derivatives. Derivatives of the function with respect to each input variable, assuming all other inputs are constant. And when we compile all of these partial derivatives as a vector to make a vector field, we get the gradient. The gradient points in the direction of greatest change of the value of our function. You can think of each of these partial derivatives as moving along the axis of that respective input variable. This would be moving along the x-axis, this along the y-axis, this along the z-axis, and this along the w-axis. If we have too many input variables, it becomes impossible to visualize. So for demonstration purposes, let's stick with just two input variables and one output. This way, we can graph our function in 3D space, and we can graph its gradient in 2D space. Let's use the function f of xy is equal to x squared plus y squared to demonstrate gradients. If we take the gradient of this function, we get the following vector field, where each vector in space is defined by twice its horizontal x-coordinate and twice its vertical y-coordinate. Now, let's draw some random curve c in our gradient field and try to find its line integral. Let's make this curve the line segment of y equals x squared, going from 1, 1 to 2, 4. Once we take the line integral of our gradient field over this curve c, and the details of this are not particularly important, we find that our line integral is 18. Interestingly, if we plug in the endpoints of our curve c, 2, 4 and 1, 1, into our original multivariable function f, we get 20 and 2. And their difference is the same as our line integral. This, ladies and gentlemen, is the fundamental theorem of line integrals. Written formally, the theorem looks like this. Let's put this equation into words, just as we did with the fundamental theorem of single variable calculus. The integral of the gradient over the integrating curve is equal to the original function at the curve's endpoints. Let's add this to our formulas dictionary. For the last three theorems, I'm not going to go into as much detail on the specifics as I did for the previous two. There are plenty of incredible videos out there visualizing these theorems in different ways. Instead, I'm going to focus on the bigger picture so we can get an answer to our initial question. How does multivariable calculus all come together? Now let's talk about Green's theorem. The formula for this theorem looks like this. Looking at this for the first time, it can be difficult to understand exactly what's going on here, especially if you're not familiar with double integrals. Let's break it down. For this theorem, we're still just working with the 2D xy plane. On the left side, we have a line integral over a curve c, just like before. Except now, instead of finding the dot product of a vector field and a derivative vector, we multiply each component of the vector field by the differential component in its respective direction. Mathematically, it's the same operation, just written differently. We multiply the horizontal part of our vector field by a differential movement in the horizontal direction along c, and the vertical part of our vector field by a differential movement in the vertical direction along c. Then, we add up all those products over the entire curve c. This circle here means that our curve is closed, and that we want to take the line integral over the whole closed curve c. On the right side, we have a double integral over an area d. This area is enclosed by our curve c, and we're taking the integral of this weird combination of partial derivatives. It turns out that this combination of partials can be interpreted as a measure of how much a vector field curves or curls. You can think of this as a tiny circle vector existing on a differential area component like this. All the double integral says is that we need all of these tiny curls times the tiny area component they are on in both the x and y directions separately, which is what it means to integrate over an area. It's basically just two consecutive integrals. First, take the integral with respect to x, get some result, and then take the integral of the result with respect to y. The conceptual idea behind Green's theorem is that adding up all of these little circles of a vector field inside an area is the same as taking the total curvature of the vector field along the shape's boundary. Going back to the raw equation, we can put it into words, just as we did with the other two theorems. The integral of the derivative over the integrating area is equal to the integral of the original function over the boundary curve. Let's store this statement away in our formulas dictionary as well. Moving on to Stokes' theorem, the equation is written like this. Notice that the line integral on the left side of the equation is exactly the same as the line integral in Green's theorem, just written differently. The right side is still a double integral, but now we're taking the double integral of something else. Graphically, we're still dealing with a 2D shape enclosed by a 1D line, except now our 2D shape can live in 3D space if we so choose, making it a surface rather than an area. This weird value inside the double integral is actually called the curl. The curl is essentially another form of a derivative. Like the gradient, it involves partial derivatives, except this time it's of a vector field and we're multiplying those partials in a weird way. Again, the details of how we calculate curl are not important. What is important is understanding what curl is intuitively. Curl is actually a vector field. If we have a portion of our initial vector field in 3D space that curls around like this, the curl vector points perpendicular to our vector field, and its magnitude measures how much our vector field, curls or curves around in circles. This concept is exactly the same as the weird derivative expression in Green's theorem. In fact, that expression is equal to the curl of a two-dimensional vector field. So really, Green's theorem is a special case of Stokes' theorem, where our surface only exists in 2D space. The other important part of the double integral is this ds component. It tells us that we're taking what's called a surface integral, an integral over surface. The differential components of our surface area are small surface patches, and we describe these with vectors of infinitesimal magnitude pointing perpendicular to our surface. This is ds. We take the dot product of these surface vectors and the curl, which points perpendicular to our vector field, and sum them all up over the whole surface. So altogether, Stokes' theorem tells us that if we have a 2D surface existing in a 3D vector field, adding up all of the tiny curls of the vector field over that surface is equal to calculating the curve of the vector field over the boundary of that surface. Let's put this formula into plain English as we did before. The integral of the curl over the integrating surface is equal to the integral of the original function over the boundary curve. Let's store this away in our formulas dictionary. Finally, we have the divergence theorem. This theorem is another higher dimensional extension of the theorem of line integrals and Stokes' theorem. First, we dealt with integrals over lines, then integrals over surfaces. Now we're going to look at integrals over volumes. The equation for the divergence theorem can be written like so. On the left side, we have a double integral over a surface S. On the right side, we have a triple integral over a volume E. A triple integral is an integral in 3 dimensions, similar to how a double integral was taken in 2 dimensions. Visually, the volume we are integrating over on the right side is enclosed by the surface written on the left side. Unlike Stokes' theorem, instead of taking the double integral of the derivative form, we're now taking the double integral of the vector field itself. Our derivative form is inside the triple integral. This derivative form is called the divergence. The divergence of a vector field is similar to gradient and curl in that it's another way of taking the derivative, except it doesn't return a vector field, but instead a scalar function. It's also much easier to compute. The divergence is just the sum of all the partial derivatives of a vector field. Conceptually, the divergence measures how much a vector field points towards or away from itself. Visually, this means that if we take an infinitely small cubic volume, dv, a vector field with a large positive divergence around that dv would have a lot of vectors pointing out of the volume in all directions. So we would call it a vector source. A vector field with a large negative divergence around that dv would have a lot of vectors pointing into the volume in all directions. making it a vector sink. The right side of this equation is telling us to multiply the divergence of our vector field by the infinitely small volume components, and then add them all up. So really, it's giving us the sum of how much the vector field points outward in each tiny volume inside our 3D shape. The other side of this equation is a closed surface integral. Like the regular surface integral we computed in Stokes' theorem, we're taking differential area components on our surface, represented by a vector perpendicular to the surface, and finding their dot products with the vector field at a given point, then adding them all up. Except this time, our 2D surface is closed because it surrounds a fixed volume. The 2D surface in Stokes' theorem did not enclose any volume. In a way, the surface integral of a closed surface is a measure of the vectors pointing out of the surface. This is also known as the flux. So altogether, the divergence theorem is telling us that the sum of all the little pointed outwardnesses of a vector field inside a 3D shape is equal to the total pointed outwardness of that vector field over the boundary of that shape. Let's put this equation into plain English as well. The integral of the integral of the integral of the divergence over the integrating volume is equal to the integral of the original function over the boundary surface. This statement can also be added to our formulas dictionary. In fact, let's take out all the statements in our formulas dictionary and analyze them now. Well, this just looks like a lot of words. We can use what I like to call the mathematical properties of the English language to simplify these sentences. If we see two of the same word or phrase on either side of an is equal to phrase, we can cancel them, just like we would with a mathematical equation. If we look at these last three statements, we can cancel one or two integrals on either side of the is equal to, so we are left with this. Now, let's generalize some of these nuances here. Over the integrating curve, the integrating area, the integrating surface, the integrating volume, curves, areas, surfaces, and volumes are all things we integrate over, and we can generalize them as shapes. In the same way, the endpoints, boundary curve, and boundary surface are all just boundaries, so we can simplify them like so. And finally, we know that the gradient, the curl, and the divergence are all different forms of the derivative, so we can generalize them to just the derivative. And now we see a pattern emerge. The integral of the derivative over a given shape is the original function at, along, or over the shape's boundary. This, my friends, is what connects all of multivariable calculus, how it all comes together. Take a moment to let this sink in, and maybe go back to other parts of the video to brush up on the theorems that led us to this idea. Luckily for us, some genius mathematicians have generalized this into a nice and neat formula called the Generalized Stokes Theorem, written like this. The Generalized Stokes Theorem states that the integral of a differential form over a boundary d omega of some orientable manifold omega is equal to the integral of its exterior derivative over the whole of omega. Now, I know that was a mouthful, but this is it. This one equation lets you generalize all of calculus in any number of dimensions that you want. Let's analyze it a bit more thoroughly. As a disclaimer, I have not taken differential geometry, so I'm not really in a place to rigorously define an orientable manifold or an exterior derivative for you. But the core idea in this equation is exactly what I've discussed throughout this whole video. You can think of this differential form as just the function or vector field that we are integrating over. What's special about this differential form is that, well, it's differentiable, or in other words, has an exterior derivative. For the fundamental theorem of single variable calculus, the exterior derivative is just the normal one-dimensional derivative we think of as a slope. For the fundamental theorem of line integrals, the exterior derivative is the gradient. For Green's and Stokes' theorems, the exterior derivative is the curl. And for the divergence theorem, the exterior derivative is the divergence. Omega here is the shape we integrate over, and d omega is the boundary of that shape. For line integrals, omega is the integrating curve, and d omega is its endpoints. For Green's and Stokes' theorems, omega is the surface we are integrating over, and d omega is the closed boundary curve of that surface. And finally, for the divergence theorem, omega was our integrating volume, and d omega was the surface enclosing that volume. The single integrals on either side of this formula are really just truncated representations of multiple integrals, with the boundary side of the equation always being one integral less than the shape side. Putting all that together, this theorem is the ultimate culmination of the pattern we observed among all the theorems of multivariable calculus. The integral of the derivative is equal to the original function along the boundary. I'll say that again, just for emphasis. The integral of the derivative is equal to the original function along the boundary.
And that's it. If you've made it this far, congratulations. You just have everything you need to know to have the theorems of vector calculus ingrained into your mind. And if you still don't get it, that's okay too.
This perspective on multivariable calculus only came to me about 6 months after the end of my course. It happened right outside my college dorm in a car at 1 a.m. with 3 of my friends. One of them was stressing about his upcoming multivariable calculus final, and so my other friend, a senior and another physics and CS major, was trying to console him. In doing so, he said something along these lines.
In higher math, all of those theorems, the theorem of line integrals, Stokes' theorem, the divergence theorem, they're all the same thing.
He then proceeded to explain everything I described in this video with a lot of finger motions. I mean, physicists are quite good with their fingers. Not that I would know, I'm just a foolish chemist. The reason that my second physics and CS friend was able to enlighten me that night was partly because he had taken higher level math, so he had the perspective on Calc 3 that stems from the Generalized Stokes Theorem. It was this perspective that he shared with me that night that stuck with me forever.
I mean, it's what took me from here to here. Goes to show that sometimes all you need to solve a problem is to look at it from a different angle.
To me, it's crazy to think about how all 5 of these complicated theorems can be generalized so simply. Take it from a guy who doesn't even study math. I'm a chemist, and I still spent all of this time making a video about math because it was a topic, a perspective, that I found earth-shatteringly awesome. Truth be told, the Generalized Stokes Theorem really just reflects one of the greater themes of math. The more math you learn, the more you realize everything is the same. In a way, you could say that all of math converges to that one astronaut meme. That's impossible. It's all Stokes' theorem? Always has been.
And so, to be honest, if you're going to take away only one thing from this video, it shouldn't be that the integral of the derivative is the original function at the boundary. It's that you should find yourself a physics and CS friend in college.